Hello, today we're going to look at a basic introduction to the nuclear shell model. The shell model is one of a number of models used to describe the nucleus. These are called phenomenological models, and what they do is they describe the nucleus as if it were something else by analogy. So in this case, the shell model describes the nucleus as if it were behaving like electrons in shells around an atom. The purpose of all these models is to help us to understand and explain the behaviour of the nucleus. Now, we have seen from previous videos that the basic structure of an atom is that there is a central nucleus, which we'll talk about in a moment, with orbiting electrons. And there may be many electrons orbiting an atom or orbiting a nucleus. The nucleus itself consists of protons and neutrons. Protons are positively charged, neutrons have no electrical charge. And the question that we had to ask ourselves is, how can it be that a nucleus that has got a number of protons does not self-destruct, because the Coulomb force of repulsion should make sure that all positively charged protons repel one another. But clearly that is not what happens. And so we have to say that at least over the range of the nucleus, there must be a force, which we call the strong nuclear force, which is able to hold the protons together and is stronger than the Coulomb force, which is tending to push them apart. We are aware from the videos that we have done on atomic physics that electrons orbiting a nucleus do so in well-defined energy levels. And what we say is that no two electrons in any single atom can occupy the same energy states. Or to put it another way, no two electrons can have the same four quantum numbers. We'll talk about those in a moment. Now, it might initially have been thought that whereas electrons are required to occupy their own energy levels because they're not allowed to be in the same energy state, they're not allowed to have the same four quantum numbers, that might not be true when it comes to the nucleus. In fact, you could consider the nuclear force as simply being a kind of a bag which holds all the protons and the neutrons together, squashed together, so there's no room, and they all just sit there quietly and stably inside this nuclear force which stops them from getting out. However, we know that in relation to electrons orbiting nuclei, you can, if you give them sufficient energy, kick the electron out of the atom altogether. That can be done, for example, with the photoelectric effect. If you take a sheet of metal and you shine light on it, that light usually has to be in the ultraviolet range, then you get electrons coming off. This experiment was one of the forerunners of the development of quantum mechanics. And what is actually happening is that a photon of the ultraviolet light is transferring its energy to the electron, and provided there is enough energy in that photon, the electron can be kicked out of the atom, out of the binding of the nucleus. The nucleus is exerting a positive force on this negatively charged electron, causing it to stay in the atom. But if you give it enough, if you give the electron enough energy, you can kick it out of the atom altogether. And that's what's happening here. It's the photoelectric effect. Now, in a similar way, you can also kick a nucleon, either a proton or a neutron, out of the nucleus if you give it enough energy. The difference here is that, for example, if you take a hydrogen atom and you have an electron in its ground state, then to kick an electron out of a hydrogen atom, you need 13.6 electron volts of energy. But if you want to kick a proton or a neutron out of a nucleus, you will need energy in the range MeV, millions of electron volts. So significantly more energy is needed. Now, if you plot the energy required, this is the energy required to kick one electron out of an atom, and on this scale, you put the number of protons. So essentially you're putting the elements along the bottom, starting with hydrogen and going maybe all the way up to uranium. And what we're going to do is to kick one electron out of each of these atoms, and you measure the amount of energy you need to do that. What you find is that you get a graph that looks something like this. It's not quite as obvious as this, but it has this kind of shape to it. You get peaks. And what you find is that those peaks correspond to what are called the noble gases. That's helium, neon, argon, krypton, and xenon. And the qualities of those gases, and the reason they're called noble or inert gases, is that the rings of electrons around those nuclei are full. There is no space for any spare electrons. All the rings are complete. And the argument is that when you have complete rings of electrons, that is to say all the shells are completely full in the electron shells, there is an additional energy or a binding energy which binds those electrons all the more closer to the nucleus. And consequently you have to put in a lot more energy to get an electron out of one of these gases than you would for, say, an element right next to helium or an element right next to neon, where the binding energy is significantly less. You don't have to put so much energy in to get one of the electrons out. And in a similar way, what is found, remember these are generally in electron volts, is that if you now, instead of trying to get an electron out of the atom, you now try to get a proton or a neutron out of the nucleus of an atom, and again we're going to look at them from, say, hydrogen up to uranium, what you will find is that again you will get this sort of shape where there are peaks, but they do not correspond to the peaks that you get for electrons. Nonetheless, it is the result, the experimental result, that if you want to eject protons or neutrons from a nucleus, then depending on what nucleus it is, all the way from hydrogen up to uranium, the fact that you get peaks of energy suggests that maybe the neutrons and protons in a nucleus are being held in shells, rather like electrons are, and that when those shells are complete, then just as the case with electrons, you need significantly more energy to get a proton or a neutron out of a complete shell than you do if the shell is incomplete. And it's that experimental result that gives rise to the idea of a nuclear shell model where protons and neutrons, instead of just being held in the nucleus as if the nuclear force were a bag holding them all together, that maybe the protons and neutrons also occupy shells within the nucleus. Now the peaks occur when the number of neutrons or the number of protons in the nucleus are equal to the following numbers: 2, 8, 20, 28, 50, 82 and 126. In other words, if you have that number of protons or neutrons in a nucleus, then you will find that you will need significantly more energy to get one of those protons or one of those neutrons out than you would if you were using, if the protons or the number of protons or neutrons in the nucleus were different from those numbers. And those numbers have sometimes been called magic numbers. And those numbers apply to protons and neutrons. So you might have a nucleus, for example, that has 20 protons and 20 neutrons, and that would be very stable. And that, of course, is calcium. Calcium has, or one of the isotopes of calcium has 20 protons, 20 neutrons. That is a very, very stable nucleus. You need a lot of energy to eject either a proton or a neutron from calcium. Now we know that when electrons are orbiting the nucleus, there's the nucleus, there's an electron orbiting, we know that the force that is keeping that electron essentially in orbit is the Coulomb force, the force between the positively charged nucleus and the negatively charged electron. That's the Coulomb potential. The question is, when you've got protons and neutrons in a nucleus, they're not orbiting anything. So what is it that keeps them inside the nucleus? And the answer is that there must be an interaction between each of these protons and neutrons, and the combined effect of the interactions between all of them is the resultant nuclear force. But this kind of picture is very difficult for physicists, because it means you have to try to model the interaction of every single proton or neutron with every other proton or neutron in the nucleus. That's called a many-body problem, and it's mathematically very difficult. And so the way that physicists traditionally have got over this problem is to say that you can take any one of the nucleons, proton or neutron, let's take that particular one there, and we say that that proton or neutron will experience a nuclear force which is made up of the total of the impact of all the other nucleons. So in other words, this nucleon is being affected by the sum total of all the rest. And that then reduces to what's called a two-body problem, and that's much more easy to cope with. And if we are arguing that the strong nuclear force, which is a force operating between each of the nucleons, is a binding force, it has to be because it's got to hold the nucleus together, then essentially we can regard this nucleon as being in a potential well. Here is the potential well, there is the nucleon sitting at the bottom of it, and that's, as it were, the binding energy. You would have to give this nucleon this much energy if you wanted to get it out of the well, in other words, if you want to get it out of the nucleus, because the combined nuclear force of all of the other nucleons essentially is what is binding this nucleon into the nucleus. And you have to overcome it with this amount of energy to get the nucleon out. Now the question is, what is the shape of that nuclear force? If we were to plot essentially the force, which we'll call V, against the distance from the centre of the nucleus, we would expect, just on the basis of basic reasoning, that the force, this is the this is repulsive up here, and this is attractive down here. Extend it down here like that. So we would expect that the force would look something like this, where this distance here is the radius of the nucleus. Radius of nucleus. Why do I say that? Well, what I'm saying is that as two nucleons get very close together, there must now be a repulsive force, because if there weren't, then the two nucleons, the protons, the neutrons, would get squashed together, squashed on top of one another. So there must be something in the nuclear force that stops the whole of the nucleus from simply being squashed down to a single finite point, or sorry, infinitesimally small point. There must be something that allows the nucleus to maintain a shape and a size. If the nuclear force were entirely attractive, then the whole thing would squash together rather like a black hole. But down here, the force is attractive. That is to say, if two nucleons are this far apart, they will be pulled together. However, by the time you get to the nuclear radius, the effect of the strong nuclear force has pretty much withered away. The Coulomb force, by contrast, looks something like this. It's a 1 over r squared term. In other words, the closer that two protons get together, the greater is the repulsive force between them, trying to push them apart. And the idea is that the strong nuclear force, this attractive force, must overcome the equivalent Coulomb force, which is trying to drive the protons apart. So we're looking for something about this shape. And when I was at university doing a PhD in nuclear physics, the shape that was often used was one that was called Woods-Saxon, or in my day it was called Saxon-Woods, but more recently it's been called Woods-Saxon. They seem to have changed billing. And the shape of a Saxon-Woods curve is something like this. It doesn't have the repulsive term that you need here because we're not worried about that. That bit is not the important thing. The really important thing is the shape of this face here, which determines the extent of the nuclear force and the way in which nucleons are held together. And you'll notice that the point about this force is that it's very strong within the nucleus, that's in this region here. But as you get towards the edge of the nucleus, it falls very rapidly to zero by the time you are just a tiny distance outside the nuclear radius. The formula which describes the Saxon-Wood or Wood-Saxon model is V, which is a function, of course, of distance, is equal to minus, because it's a binding energy, V naught divided by 1 plus the exponential of R minus R over A, where V naught is of the order of 50 MeV, capital R is 1.25 times A to the third, where A is the total number of nucleons. And if you think about it, there's some sense in that because the volume of the nucleus will be three-dimensional. We are looking at this in one-dimensional, so you take the cube root of the total number of protons and neutrons, and as it happens you multiply that by 1.25 and that gives you the term for R. And A is approximately 0.65 Fermis. And the question is, why do we need to go for a Wood-Saxon formulation with all this complication here? Why do we not simply take the famous old square well, which surely would do just as well? The trouble with that is, if you go back to the video that we did on the particles in a square well, you find that the energy levels of the particles in a square well are even. But we have found experimentally that there are magic numbers. There are certain numbers where the energy that you need is much higher than for other combinations of protons and neutrons. And so a model where all the levels are equally spaced is not going to do the trick. We need to find some kind of formulation, and that's what Wood-Saxon were trying to find, which will enable us to have variations in energy levels so that we can account for what look like shells in the nucleus. Now, with atoms, we discovered that the electrons in an atom are subject to 4 quantum numbers: the principal quantum number, the angular quantum number, the magnetic quantum number, and the spin quantum number. And no 2 electrons could have the same 4 quantum numbers. And the rules were that n, the principal quantum number, is any number from 1 to, in theory, infinity, although in fact you don't usually get much past 8 for an atom, but they must be integer. 1, 2, 3, 4, 5. The value of L is any number from 0 up to n minus 1. They can't go higher than the value of n minus 1. The values of m are any number, again integer number, from minus L through to 0 through to plus L. And the value of S, the spin, is plus or minus a half. And so we saw, I shan't go through this in much detail, we saw that when n is 1, L must be 0, because L is 0 up to n minus 1 and n minus 1 is 0. M must be 0 because M goes from minus L through to plus L and L is 0. And S is plus or minus a half. Consequently, in the first shell for electrons, you can only have 2 electrons, a plus half and a minus half. When n is 2, L can equal 0 or L can equal 1. When L is 0, M is 0, S is plus or minus a half, and again you get 2 electrons, one with plus half, the other with minus a half. When L is 1, M can be minus 1, 0 or plus 1, and in each case S can be plus or minus a half. So you've got 3 options, each with a plus or minus a half, so that's 6. So consequently, in the second shell you have a maximum of 8 electrons, and overall you have 10. If we move on to the next shell, n equals 3, then the options are that L equals 0, L equals 1 or L equals 2. If L equals 0, you're going to get exactly the same thing as here, 2 electrons. If L is 1, you're going to get the same thing here, 6. And if L is 2, then M is going to be minus 2, minus 1, 0, 1 or 2. Each of those 5 levels can have plus or minus a half spin, and consequently you get a total of 10 electrons in the L equals 2 level. That means that there is a total of 18 electrons in the third principal quantum number, and overall 10 plus 18 gives you 28. So you can see that shells are full when there are 2 electrons in the atom, when there are 10 electrons in the atom, and when there are 28 electrons in the atom. 2, 10 and 28 are, as it were, the first 3 magic numbers for electrons. But as I explained to you earlier, for protons and neutrons the magic numbers are 2, 8, 20, 28, 50, 82 and 126. So they're not the same as these. And that suggests that perhaps the protons and neutrons may have different quantum numbers. And the answer is that it turns out that the proton and neutrons' quantum numbers are not that dissimilar from those which govern electrons, except for this restriction here. In an electron, the value of L, the angular quantum number, can be anything from 0 up to n minus 1. With protons and neutrons, the value of L is unrestricted by the value of n. In other words, L can be 0, 1, 2, 3, 4, and as high as you like. It doesn't matter, it's not constrained by the value of n. And what it turns out matters in nuclei is the value of the angular momentum, quantum number, which is L, and the value of the spin angular momentum quantum number, which is S. And the idea is that you combine the two to form a new number called J, which is L plus S. The value of the angular quantum number plus the value of the spin angular momentum quantum number. And since L is always either 0 or an integer number, and since S is always plus or minus a half, it means the values of J will be a half, 3 halves, 5 halves, 7 halves, and so on. Now, in a similar way with electrons, where the number of electrons in any shell is defined by the fact that no 2 electrons can have the same quantum numbers, and therefore there's a maximum number of electrons that can be in any given shell. So in a similar way, you find that the value of J determines the number of protons or neutrons that can occupy that value of J. And if J is a half, then you can only have 2 protons or neutrons in that state. If J is 3 halves, you can have 4. If J is 5 halves, you can have 6. If J is 7 halves, you can have 8. If it's 9 halves, you can have 10, and I think you're spotting the pattern. Basically, if J is equal to x over 2, then the total number of states that you're allowed to have is x plus 1. Now, just like with electrons, the value of L determines the letter that is assigned to the orbital. So when L is 0, that is called an s orbital. When L is 1, that's a p orbital. When L is 2, that's a d orbital. When L is 3, that's an f orbital. And then after that, it just goes up in alphabetical order. L is 4 is a g orbital. L is 5, that's an h orbital. And the orbitals are then described in this kind of way. You could have a 1p 3 halves orbital. And what this is telling you is that the principal quantum number, the value of n if you like, is 1. The value of L is 1 because that's the p orbital. And the value of J is 3 halves. And if it's 3 halves, then we already know that there are a maximum of 4 states or 4 particles can occupy that level. If you had, for example, the 2p to the half, that would tell you that it was principal quantum number or shell number 2. The angular quantum number would be 1 because it's a p. The half would mean that there would be a maximum of 2 particles in that level. A 3s to the 1 half would tell you that you were in your 3rd shell. S would tell you that L equals 0, and 1 half would tell you there's a maximum of 2 particles. Or let's take a complicated one. The 4g 7 halves tells you that it's shell number 4, principal quantum number 4. The angular quantum number is going to be 4 when it's G, L is 4, and 7 halves means that there's a total number of 8 particles, 8 nucleons, 8 neutrons or protons that can occupy that particular state. And if there are 8 in that state, then that state is said to be full. And of course we've got a whole host of these shells. I've only put in a few here as examples, but remember we can have any shell number 1, 2, 3, 4. We can have any value of L, because remember for nuclei the L value is not constrained as it would be for electrons. And then we can have any value of the J number. And so there are a range of shells, and the key question is now, what order do they come in when it comes to energy levels? And this has to be determined by experiment. So I'm going to draw, this is the binding energy, that is to say, this is the energy that you would have to give to a nucleon in a shell in order to push it out of the nucleus. So this is 0 up here, and then all the binding energies are traditionally expressed as negative values, meaning that you'd have to give the proton or neutron energy if you wanted to get it out of the nucleus. And what we find is that the lowest, that is the most tightly bound energy level, is the 1s half. And the total number of protons or neutrons in a half, J equals half level, is 2. What you then find is that there's a bit of a gap before you get to the next energy level, and then there are 2 which are very close together. And those are the 1p half and the 1p 3 halves levels. And if it's a 1p, sorry, the other way around, it's the 1p 3 halves and 1p 1 half level. The 1p 3 halves level can have a maximum of 4 states or nucleons, and the 1p 1/2 level can have a maximum of 2. And if you put the two together, in that, as it were, shell, we regard this as one shell because they're very close together, you can have a total number of 6 nucleons, and therefore that if those are complete and full, and this one is full, then you will have 2 completed shells if the total number of nucleons is 8. 2 plus the 6 in this shell. There's then another gap before you get to another set of levels, and there are now 3 very close together, and they are the 1d5/2 level, the 2s1/2 level, and the 1d3/2 level. And the total number of protons or neutrons in each of these is, for the d5/2 level, 6, for the s1/2 level, 2, and for the d3/2 level, 4. And that means you've got a total of 12. And if you add 12 to 8, that means that when all 3, as it were, shells are full, you'll have a total of 20 protons or neutrons, as the case may be. There's then another gap before you get to the next level, which happens to have just one level, and that is the 1f7/2. And 1f7/2 can have a maximum of 8 states, or 8 nucleons. And if that is full, and all the ones below it are full, that means you have a total of 28 protons or neutrons in all in that nucleus. I shall just do one more level. It has got 4 levels very close together. That is the 2p3/2, the 1f5/2, the 2p½ and the 1g9/2, and they can have 4 plus 6 plus 2 plus 10 nucleons, giving a total of 22 in all. And if all those are full, on top of all these being full, then you get a total of 50 nucleons in all. Now, I won't go any further, but you can see what's happened. We have now found the magic numbers, which I related earlier, 2, 8, 20, 28 and 50. When you have 2 nucleons in a nucleus, that means the 1s1/2 is full, and if it's full, when a shell is full, it has a higher binding energy than if it were not full. Similarly, if the next 2 states, which form as essentially the second shell, if they are full, there will be 6 nucleons in that shell, plus the 2 nucleons in the first shell makes a total of 8 nucleons in all. And in the third shell, which consists of 3 separate levels, which can hold a total of 12 nucleons, if they are all full, then you get a total of 20 nucleons in the nucleus. And so this is the reason why the shell model is successful. It reveals that far from the nucleons being held just as it were all scrunched up in a bag, they actually occupy individual shells, and they have associated quantum numbers in broadly the same way that electrons do. And that should come as no surprise to us. Why should the Pauli exclusion principle apply only to electrons? We are talking here about subatomic particles, and what we've discovered through the shell model is that the Pauli exclusion principle doesn't only apply to electrons, meaning that electrons in an atom cannot have the same 4 quantum numbers, but it also applies to nucleons in the nuclei, meaning that nucleons have to occupy different energy levels because there is a limit to the number of nucleons that can be held in any given energy level because of the Pauli exclusion principle. Nucleus. The nucleus itself consists of protons and neutrons. Protons are positively charged, neutrons have no electrical charge. And the question that we had to ask ourselves is, how can it be that a nucleus that has got a number of protons does not self-destruct, because the Coulomb force of repulsion should make sure that all positively charged protons repel one another. But clearly that is not what happens, and so we have to say that at least over the range of the nucleus there must be a force which we call the strong nuclear force, which is able to hold the protons together and is stronger than the Coulomb force, which is tending to push them apart. We are aware from the videos that we have done on atomic physics that electrons orbiting a nucleus do so in well-defined energy levels. And what we say is that no two electrons in any single atom can occupy the same energy states. Or to put it another way, no two electrons can have the same 4 quantum numbers. We'll talk about those in a moment. Now, it might initially have been thought that whereas electrons are required to occupy their own energy levels because they're not allowed to be in the same energy state, they're not allowed to have the same 4 quantum numbers, that might not be true when it comes to the nucleus. In fact, you could consider the nuclear force as simply being a kind of a bag which holds all the protons and the neutrons together. Provided there is enough energy in that photon, the electron can be kicked out of the atom, out of the binding of the nucleus. The nucleus is exerting a positive force on this negatively charged electron, causing it to stay in the atom. But if you give it enough, if you give the electron enough energy, you can kick it out of the atom altogether. And that's what's happening here. It's the photoelectric effect. Now, in a similar way, you can also kick a nucleon, either a proton or a neutron, out of the nucleus if you give it enough energy. The difference here is that, for example, if you take hydrogen, a hydrogen atom, and you have an electron in its ground state, then to kick an electron out of a hydrogen atom, you need 13.6 electrons squashed together, so there's no room, and they all just sit there quietly and stably inside this nuclear force which stops them from getting out. However, we know that in relation to electrons orbiting nuclei, you can, if you give them sufficient energy, kick the electron out of the atom altogether. That can be done, for example, with the photoelectric effect. If you take a sheet of metal and you shine light on it, that light usually has to be in the ultraviolet range, then you get electrons coming off. This experiment was one of the forerunners of the development of quantum mechanics. And what is actually happening is that a photon of the ultraviolet light is transferring its energy to the electron and Hello, today we're going to look at a basic introduction to the nuclear shell model. The shell model is one of a number of models used to describe the nucleus. These are called phenomenological models, and what they do is they describe the nucleus as if it were something else by analogy. So in this case, the shell model describes the nucleus as if it were behaving like electrons in shells around an atom. The purpose of all these models is to help us to understand and explain the behaviour of the nucleus. Now, we have seen from previous videos that the basic structure of an atom is that there is a central nucleus, which we'll talk about in a moment, with orbiting electrons. And there may be many electrons orbiting an atom, or orbiting